Hi everyone, and welcome back to another AP Calculus video. Today we're going to talk about a concept that is BC Calculus only, and that is the length of a curve and the formula we're going to use to find that. So here we have a situation where a mathematician is creating a garden and wants to enclose the center with, of course, two mathematical equations. These happen to be her favorite mathematical equations. So we want to know what is the perimeter of her garden. So here's the garden, it'll be enclosed in here. So what's the perimeter around the edge of the garden so that she can purchase enough fencing to be able to enclose it? So what we need here is we need a formula to find the length of a curve, essentially. And so we know how to find the distance, a straight line distance. We have that distance formula. Well, the length of a curve formula is similar, and you'll notice a couple of similarities when we put it up here on the screen. But basically, we can find the length of a curved surface by using integrals and derivatives. And the formula that we're going to use to do this looks like this. So we've got two situations, and they're shown here with the curves. One situation is that our equation is defined in terms of x. That means we have y equals, and an equation with x in it, or f of x equals a function of x. And when that happens, we use this top formula. And you'll notice it uses a and b. Well, a and b are the x coordinates. So what we would have here is, if this was my situation, in this situation, we would want to consider this point down here. This would be a comma c, and this would be b comma d. So a and b are the x coordinates. C and D are y coordinates. So when we evaluate these integrals, we want to consider, what is it a function of? Is it a function of x or is it a function of y? And a function of x always looks like y equals, or f of x equals. If it's a function of y, then it's going to be like this blue equation where it says x equals, and then it's some function of y. And notice when we zoom into these formulas, we've got derivatives floating around on the inside. We'll notice that when we're in terms of x, we're differentiating with respect to x. So that means we're going to do our derivative just like normal. X is our variable. But over here, when we have an equation in terms of y, we will differentiate with respect to y, which means we don't have to consider the fact that we're not differentiating x. That bottom value here in our notation tells us what to differentiate with respect to. So here, my derivative would just be 2y. We wouldn't have to worry about implicit x because we're differentiating y. When the bottom part of my derivative notation matches the variable that I'm doing the derivative of, then I'm good to go. I need to do it. So what does this look like? Well, let's put it into play. I've got my two intersection points here on my graph. So all I need to do now to be able to do and evaluate these integrals is I need to find the derivatives. We're going to do the derivatives by hand, and then we'll evaluate our integrals using our calculus math 9 function. So let's go ahead and find our derivative. So the first function is this, y equals 4 square root of 2 over 3 x 3 halves. So to find dy dx, multiply halves, 1 goes away. And remember, you're differentiating, you're not integrating. When we get into this lesson, oftentimes we're in the midst of doing integrals all the time, actually finding a derivative. So you have to get your brain wrapped around, hey, it's derivative time. So now I'm going to reduce this exponent by 1 and make it a 1/2. So let's cancel, reduce a couple things. This turns into a 2, so I get 2 square root of 2 x to the 1/2 is dy dx, which I can actually simplify further into 2 square root of x. X to the 1/2 is a square root, so I can put it under there with the 2. Now I'm going to find the derivative of the other function. So dy dx dy, remember x equals y squared, so dx dy is just 2y. Well, that was easy. So now I'm ready to evaluate and put them into the integral. So let's go ahead and plug them in. We'll do the first curve, we'll do the red curve here. The length will be the integral from a to b, so the x coordinates. So 0.3 0.3571 is my lower limit. My upper limit is 1.0483. And here's the problem with this. Desmos will round, so unfortunately it's only rounding to 4 places. Really, we should be going to more than 4, but Desmos, this is what it gives me. So I'm going to use this for now. But please know that if you're ever integrating and you find the intersection values in your calculator, you should go out to a minimum of 6 places in your calculator. So here we go, the square root of, now my formula, 1 plus the derivative squared. 1 plus 2 square root of x, 2x squared, x. So now this is what I can put into my calculator and use Math 9 on. Don't worry, we're going to practice doing these integrals by hand as well. But for this one, because of the limits of integration, we're going to use Math 9 and plug it into our calculator. Using Math 9, we get that that length is 1.765. Now, if you have one of the older calculators, you can also enter it using the classic print. So if you were going to evaluate this using classic, what you would type in would look a little bit like this, and you should get the same result. So it's the function, comma x, comma a, comma b. So this is how we evaluate this. So 1.765 to 5 is what I'm going to write down. I'm going to go to at least 5 or 6 places in my calculations before I get to the end, and I don't round until the. So now let's do the length of curve for the other one. So this length, the blue length, is going to be from the y-coordinates negative 0.598 up to 1.024 times the square root of 1 plus, and then we're going to do 2y squared dy. Now notice it's just nice and simple. So when I use my calculator to evaluate this, I'm going to use the same process. I'm going to use the letter x though instead of y because my calculator really likes that. So I'm going to go back to my math print. I prefer that mode. It's a little easier to see. But basically you're going to go Math 9 and you're going to type it in the same way that we did with the other ones. And you're going to type in your limits of integration here. So negative 0.598, 1.024, and then in here you got to be really careful when you're typing this in. Square root of 1 plus, put parentheses around it, 2, and I use the x letter. Just use letter x, it's fine. And then dx. So when you enter anything using y into your calculator, you're going to have to use the variable x because that's the variable that it understands. So this is my length of curve, 2.2526. So my perimeter is going to be the sum of these two. When I add this together, plus, I like to scroll back up, hit enter. It's always a really good habit to do. 4.018. And whatever units that is. So I don't know, it's some sort of units that she's using. It's probably not feet. And perhaps this was a terrible example. It could be also scaled. Maybe it's, 4.018 here on my graph, the way that she has it graphed. Maybe she scales it up and she says, oh, well, each unit is worth 3 feet or something. Then you'd have 12 feet. So that's how we find the length of curve for nonlinear problems. So not a straight line between the 2 points, it's a curve. It would be like laying a string around the curve, measuring that string. So let's go ahead and practice a little bit more. Let's try this one. So this is a little bit different of an example. It says x equals this function. So right off the bat, I'm going to know that I'm going to use, because it's x equals, I'm going to use the second formula that's in y. So here we go. Find the length of the curve if x equals this. Okay, so my formula, I'm going to start by writing it down. the length of the curve that I'm going to find is going to go from negative pi over 3, pi over 4. So that's what these are. This is my C and my D. And it's going to be the square root of 1 plus the x dy. So the derivative of this squared y. Okay, so I need to find d dy. This. Ooh, this looks familiar. This is the fundamental theorem of calculus, part 1. It says this, hey, when you do the derivative, and notice you've got y dy, when you do the derivative of a function that's going from 0 to y, essentially they kill each other out. You know, the derivative and the integral kind of undo each other. That's the whole purpose of the calculus. And you essentially are left with an equation, secant squared y 1. So this is dx y. Ooh. Okay, so now let's plug that in and work it through. So my length of curve will be negative pi over 3 to pi over 4. And I'm going to have the square root of 1 plus. All right, so my derivative was secant squared y minus 1. Squared y. Now I can't plug secant squared into my calculator. So I'm going to have to work around that. So what I'm going to do is I'm going to rewrite this as 1 over cosine squared. And as a matter of fact, I'm not even going to write it as 1 over cosine squared. I'm going to write it 1 over cosine of y with parentheses around it squared. So that's how I'm going to enter it into my calculator. And it should look a little something. Now when I enter it in, I need to be super careful about all my parentheses and remembering to square the derivative. So, oh, and look at me, I even forgot the minus 1. So look how easy it is to accidentally forget things. By the way, you can use this second delete button to insert things. So minus 1, there you go. And now that is squared together. So I'm using x instead of y when I'm typing it in, and I'm super careful about enclosing everything. So 1 divided by cosine of x squared minus 1 squared. So that is my function, and when I hit enter, it'll spit out my answer. I want to make sure that I am in fact in radian mode. Excellent. So 2.221 is the length between negative pi over 4. So this is our length of curve formula, and the trickiest part is finding that derivative. And for a problem like this, we had an integral and we took the derivative of the integral, and so it was just the function itself. But you always have to remember, you know, if we go back to up here, we had to find the derivatives. The derivative of the function is what you plug in. You're always going to have to do the work for the derivative and find that by hand. And then half the time you'll be able to do Math 9 to evaluate the integral, and the other half of the time you're going to have to continue to do everything by hand. But basically, the derivative that we do will be something that we do. Let's practice one more where we're not going to be using our calculator. So we're going to use analytical methods to complete this one. So no Math 9, analytical means by hand. So first things first, this one's y equals. So I know that I'm going to be using the derivative with respect to x, and I'm going to use the x coordinates, basically what's given to me. But essentially, I'm going to find dy dx. So it's 3/2 x to the 1/2 power. So that is what I'm going to be plugging in. So the length of curve is going to go from 0 to 4, the square root of 1 plus my derivative, 3/2 x to the 1/2 squared dx. Now, no calculator means I'm going to have to do some algebra on the inside. So this becomes 0 to 4, 1 plus, when I square everything inside, this becomes 9/4 x dx. So the squaring of the x to the 1/2 just becomes x, but I need to remember to square both of the numbers. So now I've got this integral, and this is simply a u substitution problem. So here we go. U equals 1 plus 9/4 x du equals 9/4 dx. So I'm going to have the integral of u to the 1/2 power. And I'm going to replace, let's see, I'm going to move the 9/4 over, it becomes 4/9 u. When I divide by 9/4, it's the same as multiplying by that reciprocal, equals dx. I'm going to have 4/9 u. So now I'm just going to integrate that, 4/9. This becomes u. Now I'm integrating, not differentiating, so you always have to wrap your brain around integrating increases. So u to the 3/2 over 3/2. So then that 3/2 will flip, multiply. So we ultimately get 8/27 u to the 3/2 power. So now that I have my antiderivative, I'm going to put u back in. And it's going to look like this. The integral from 0 to 4. Actually, I'm done integrating. 8/27 1 plus 9/4 x to the 3/2 power. And I'm going to evaluate that from 0 to 4. Okay, getting ugly, but that's okay. We can handle this. A little bit of arithmetic. I'm going to put 4 in. 8/27 kind of hangs out. So I'm going to factor that out, so it makes it a little easier to work with. So I'm going to have 1 plus 9/4 times 4 to the 3/2 power minus 1 plus 9/4 times 0 to the 3/2 power. Okay, so it's not so bad after all. These cancel out. This becomes 10 to the 3/2 minus becomes 1 plus 0, 1, 8/27. And actually, this is kind of where I'd stop because I'm to a point now where I can't do any more. I've plugged things in. And actually, I probably could have stopped here and been just fine. But I went one step further, and I think that's as good as we get. And we can always use Math 9 and double check our work in the time that we're learning or practicing. But basically, this is how you find the length of a curve. Any sort of problems involving perimeter on a free response question in AP Calculus is going to involve this length. And yes, you need to memorize it and know it for your exam. Do not get a formula. Just remember, it's the integral from limit to limit, from endpoint to endpoint. It's in terms of x, it's all x's. X endpoint to x endpoint, the square root of 1 plus the derivative squared. And that is my noisy door. So I apologize for that. But here we are at the end of the video. Nothing like somebody ringing your doorbell to tell you that time is up. So again, it's just the square root of 1 plus that derivative squared. Please don't forget to square your derivative and then use your proper limits of integration depending on whether it's x or y values. So that's it. A little bit of practice. You guys will get there. It's not a complicated topic. Just the algebra involved can be. So keep at it. Keep practicing. You're going to get it. You've got this.